Hello there. Today we're going to take a brief look at GSM-Symbolic, understanding the limitations of mathematical reasoning in large language models. This paper is out of Apple, which continues to slowly but surely enter into the research area, obviously with personal acquisitions like Sami Benjo, who was previously at Google. This was to be expected, but still very cool that more companies are coming out and doing research in this field, especially now that the traditional companies such as OpenAI and Google are going more out of the research fields and only releasing technical reports, aka advertisements about their new APIs. So what does this paper do? In short, this paper questions whether reasoning is happening in large language models, especially as it pertains to mathematical reasoning. They also ask a little bit the question, are the current benchmarks, notably the GSM-8K benchmark, are the current benchmarks sort of part of the training sets of a lot of these models? Because some of their experimental evidence suggests that the models might already have pre-knowledge of the questions. And lastly, they investigate, how robust are LLMs to kind of this mathematical task? Do they really understand these things, or do they just sort of do pattern matching? And the conclusion that this paper comes to is obviously that, oh no, the LLMs aren't reasoning. They are just quote unquote pattern matching. And also there's probably quite considerable amount of training set poisoning or test set poisoning, however you want to call it, of this GSM-8K benchmark. And therefore new data sets, new benchmarks are needed. And they provide one of those. This GSM-Symbolic is one additional data set or methodology of creating synthetic data that's supposed to prevent this type of training set conflation or test set conflation. All right, so a lot of stuff packed into one paper. Nevertheless, it's quite a short paper, and I expect we won't spend too much time. The problems I have with this paper are twofold. On one hand, I do believe their dataset construction of this GSM-Symbolic dataset is not without problem, and we can discuss that. So some of their conclusions, I would put like a question mark behind them, just because of how they constructed their dataset, and I don't agree with their kind of assumptions behind that. And secondly, their whole point about reasoning as such. Now, it's totally fair to provide research that kind of shows the weaknesses of LLMs in a given task, and also maybe even why those weaknesses appear, as this paper does. But then to draw kind of conclusions of, oh, it's not reasoning, it's just pattern matching, and so on, without defining reasoning, without defining these terms well, is a bit shady. So the question you have to ask yourself is, are humans reasoning? Just try to, and then you're going to first make a joke and say, oh, well, some aren't, ha ha ha. But, if you actually think about it, you probably say yes. You probably say humans, sort of the human brain is reasoning in its assessment of problems. Now, this is a challenge for this paper, because I would say, yeah, if you gave the tasks here to a human, they would probably fail in a similar way. And therefore, if this paper concludes that since the LLMs fail in these ways, they aren't reasoning and just pattern matching, I don't know. What does that mean for humans? Well, okay, let's cut it down. They are producing a new data set, and the data set is synthetic. And the dataset is made such that you can kind of produce endless variants of the same problem, but with kind of minor changes to explore how robust LLMs are to these changes. So they're going to take a example from GSM-8K, which is a human-created dataset of mathematical tasks, so little high school math questions. For this, when Sophie watches her nephew, she gets out of yada yada. This has 31 blocks in it. Animals has 8 stuffed animals inside. This has 9 multicolored rings. So it's questions where you need to know the 4 basic operations like addition, subtraction, multiplication, and division in order to reach the answer. And it's packed in a little bit of text, so you have to parse out how the different things relate, then do the calculations, and after that you'll get an answer. So the dataset has the question. The dataset also has the kind of solution process annotated, and then obviously the final solution here. So this is a good data set for exploring these topics because it's obviously relatively easy to automatically check whether an LLM did the right thing, which in the LLM world is a considerable challenge to check whether the output is correct or not, because you can formulate stuff in many different ways, but having, mathematical tasks makes this a lot easier. So what they're doing is they're always going to take a sample of GSM-8K and then kind of make a template from that. So you can see here, they annotate these kind of things. So in this case, it is names and entities and so on, but then also different numbers. So they give these all names. You can see right here, the numbers also get variable names, and then they define how these things could be filled in. So for example, a name could be any of a list of names they have internally. Then family relationship could be, in this case, so that the person who kind of makes the template here provides these things and essentially says, well, what are the things that can be filled into the template? You can see, especially for the numbers, obviously you can kind of give ranges between which the numbers can be filled in, and then you can have conditions. So the condition is one of the conditions is always what is the solution. So in this case, the solution must fulfill this condition right here, but you could have different conditions so that the problem makes sense or something like this. But this is the basic structure of what they come up with. So they take a sample of GSM-8K, make a template out of it, annotate the template with the sort of valid values and conditions on the template parameters. And after that, they have a template. And they can generate as many variants of this as they want. But note, it's always kind of the same, like the text in between the template variables is always the same. So they're taking, I believe, 1,000 or 100 of these, 100 of GSM-8K, and make these templates, or 1,000, and then always make, that's it somewhere, always make 50, I believe, variants of each. So you end up with 50 data sets, essentially. So here, for this work, we conduct nearly 500 total evaluations, yada, yada. A manageable data set size using 100 templates and generating 50 samples per template, resulting in 5,000 total templates for each benchmarks. Therefore, we have 50 data sets of 100 examples each, where each example is a mutation of one of the original 100 samples from GSM-8K. So there are 50 data sets. Each of these 50 data sets contain the exact same tasks. So task number 1 is always based on the same GSM-8K template, but filled in with different template placeholders, and therefore is kind of a different task. Now, the first question is, okay, let's give all of these 50 data sets to the LLMs, and let's see how they perform. And you will be either shocked or not shocked. I don't know what you expect, but it turns out that most of the LLMs, first of all, there's 2 effects. You see that here. Most of the LLMs have quite a variety, a variance in their final performance. So you run the 50 datasets. For each of the 50 datasets, you calculate the mean score, and then you plot that in a histogram, and you can see that the variance of these things is huge. So from a score of 70 to a score of 85, that is a much broader range than the individual LLMs are apart from each other on the leaderboard, right? Also, you can see that for a lot of the models. Now, to be said, the stronger models, so the larger models, for example, GPT-4o, you can see right here, their variance, as you can see right here, is quite a bit smaller than the the smaller models, if you will, or weaker models, however you wanna call it. So that's one thing that they point out, is that the variance is really large, but the kind of bigger model like GPT-4o is smaller. Although I do have something to say about that, but we'll get to that in a bit when we talk also about the drop in accuracy. Yeah, we'll do that now. So the second thing, as you can see, the dashed line here is always how well they did on the original data set. So on the original GSM, so if you give them the original tasks that they're derived from, how well are they doing? And you can see for a lot of models, that is quite a bit better than these dataset variants. So that's the first indication that where they say, hey, there's probably something where that the models already knew about the dataset, right? Like, why else would it be so much better on that one particular variant rather than all the other variants? So they essentially say, look, our dataset is essentially a distribution of datasets, and the original GSM-8K is basically a single draw from GSM-Symbolic. So we would expect that this falls somewhere in the middle, but it doesn't. It tends to be on the very right-hand side, meaning that oddly, in this single draw from this distribution, the models perform significantly better than they perform in all the other draws of the distribution, except a few outliers you can see, like GPT-4o and so on. So this is a graph where they show how much each of the models kind of drops on average compared to their original performance on GSM-8K. So you can see this is GSM-8K to GSM-Symbolic accuracy drop. Sorry, having trouble. This is a bar like this. Yeah, you can see that that some models like GPT-4o, O1 Mini, and so on, they have a relatively small drop in percentage, but then you have larger and larger drops, as I said, especially as the models get smaller. Now, I have something to say about this graphic. What they're making it seem like there's a difference in how much these models drop. And that's true, but also, as you saw before, for example, GPT-4o's baseline, like GSM-8K baseline performance is already at 95, whereas, for example, Gemma 2 here its baseline performance is at only 80 something, right? And then 535, its baseline performance is also like at 87 or something like this. Mistral or Mathstral is at 80. So compare a model that is at, let's do it really, really extremely. So let's say model 1 is like 99% accurate, and model 2 is 10% accurate, right? Now, imagine what a drop by 1%, and it's unclear what 1% means in this sense, but let's just say they drop by 1 percentage point, right? So this goes from 99 to 98% accuracy, and this one goes from 10 to 9% accuracy. If you look at the other way around, the error, so this doubles the error, right? So how much error M1 makes is doubled. This one here, the error was at 90%, and it's now at 91%. So this is barely like a 1% increase. This is a 1 to 2% increase in error. So if you look from that way, the models who already start at a much higher baseline performance, you kind of have to normalize their accuracy drop, if you will, by their, how much error are they making. I think that helps a lot more than looking at what their score is and looking at the reverse, what their error is, and then normalizing by that. And then I don't know if you can make too much sense out of this graph. If you rescale it by the error, they could just all be relatively constant in how much they drop. And likewise, if you rescale this variance here by the baseline error that the models make, then you could just find that, well, all of them exhibit about the same variance normalized by, you know, where they are on the error scale. So it's kind of, so there's no big point here. I just wanted to point out that graphs like this, where you look at relative performance of models that already start at different starting points, can lead you to different conclusions depending on how you scale and what your relative comparison point is. So keep that in mind. That being said, they obviously say, hey, look, since all of these kind of drop, it could be that the data set is already, the test data set is already part of the training data of these models. Now, I have maybe a bit of a different hypothesis, and they are not exclusive, so both could be part of this. But if you look at how they construct their data set, I want to challenge a bit that they say, well, our data set is essentially a distribution of data set, and the original data set is just one draw from this distributions. And I would at least slightly disagree with that. Why? Because the original data set was made by humans. And humans, when they do little math exercises, they will naturally kind of put the numbers so that they kind of make sense, both to each other and in the real world. And also maybe so that maybe it's a bit nice to compute. But especially the first two, right? If you say, well, I don't know, the electricity bill is this high, and 1 kilowatt hour of power costs this much, and those numbers, when humans make these exercises, the numbers that come out kinda make sense in the real world, right? For example, in this case right here, so right, the bin of stuffed animals has X animals inside. The tower of stacking rings has X multicolored rings on it. You can see the ranges here go up to 100. So which stacking tower of rings has 100 rings on it? So I'm not hopefully not nitpicking here, and maybe this example is just one example, but you can see that, especially then if you just sample from these ranges, right, then the relations between them are also completely inconsidered in these conditions down here. You can end up with questions that you would kind of be like, really? Why is someone buying 3,000 liters of milk exactly to go with 1 box of cereal? And why am I saying this? Because LLMs aren't just mindless calculators. LLMs are trained on human-produced text, largely. They are trained to act and predict next tokens in a world of text where that largely is from humans, for humans, and largely describes the real world. So also they will be more comfortable in, let's say, real world circumstances where things, quote unquote, make sense. So I hypothesize that at least some of the drop in performance, if you will, comes from the fact that their template generated data isn't from the same distribution as the original GSM-8K, but is from a slightly different distribution where illogical scenarios are as much part of the distribution as logical, well, kind of world-fitting scenarios are as much part of the distribution as world ill-fitting scenarios. Whereas in the original data set, they are naturally world-fitting because humans produce them. So I hope that is kind of brings the point across. The other thing is this GSM symbolic template, they are kind of half automated. So they're kind of half automated and then kind of checked by humans, but also checked by like if less than 2 models pass them, then they're checked again and so on. So it's kind of a half automated process to even come up with the data set. And then obviously sampling from the data set is a fully automated process. All right, let's go on. They do an interesting experiment where they say, hey, we just kind of sampled all of these placeholders, but we have distinct placeholders. Some placeholders are numbers, right? I can change the number of stuffed animals, the number of rings on the tower, and so on. Or I can change the names. So instead of Sophie, it's John. Instead of Sophie's nephew, it's Sophie's brother, or something like this. What if I separate those and I research those individually? You can see that if you only change the names, then the language models tend to not drop in accuracy. In fact, some of them are even better than their baseline performance. So if you just change the names right here, the green bumps, then everything kind of is fine. You still have the relatively big variance, although not as much, and everything is kind of fine. However, if you change the numbers, right, you see the blue hump here, then performance drops significantly. Also here, either it could be an indication that yes, indeed, the models have seen the test sets in their training data and they're just kind of recalling this is the one about the rings and the stuffed animals, and I recall that the answer was 14, and therefore if you change the names, they still get it correct. Or it could be that, because if you change the numbers, you make some of these samples kind of illogical. It could be that that's part of the reason. I think something that does support at least my hypothesis a little bit is that if this was really a function of remembering, you would, I don't think the variance would blow up so much. I don't think the variance would increase. You would maybe see the same bump, but maybe lower. No? Although I do have to point out, obviously, here you can see the same thing. The lower these bumps go, the bigger variance they have. And again, if you think of just rescaling it by the baseline error rate, it is not clear that variance would also increase in that rescaled version. In the rescaled version, these bumps would probably, or maybe all, be relatively the same. But yeah, I would expect even in this scaling right here, if it was a pure remembering thing, you would just take that bump and you would just shift it down, because it's always going to give the same answer, right? Because it remembers. And then, so it will be kind of the same distribution, except worse. No, that doesn't make sense, because the distribution is how much it got correct. Yeah, it could be either. I'm going nowhere with this, I'm sorry. But yeah, I hope you can see how again, interpreting these graphs is not as straightforward, I find. And the paper just, chooses one view here. All right, then they go on and say, we can now change the data set slightly, in that we can make this stuff less and more difficult. And by less and more difficult, we don't mean, it's weirder numbers or something like this. But they can now change the questions, for example, to take away a condition or one element of the question. So you have to do less math operations and consider less things, or they can add conditions to it. So here you have an example. This is a call from a phone booth. You have to pay this much for each minute of your call. The price drops after 10 minutes. How much would you pay for a 60-minute call cost? So in this sense, they could either drop this after 10-minute price drop, or they could introduce a new price drop even later. So after 25 minutes, the price drops even more. And they can do it twice. So they can say, well, after 25 minutes from the start, the price drops even more. And if your total bill is more than $10, you get a 25% discount. So the second bit here is an even new condition. So this is kind of -1 condition, easier, +1 condition, harder, +2 conditions, the hardest. So now the question is, how do the models perform if you make stuff easier and if you make stuff harder? Again, let's first look at the results. So predictably, stuff gets worse. And what they argue, they kind of argue that, well, if the models would understand, that would reason, then it shouldn't matter. It shouldn't matter how many conditions you put here. It's all just, you just map them to plus and minus and you'll be fine. So if these were actually reasoning models, then this drop in accuracy wouldn't happen. They again point out that the variances go up as you go to the left, but again, I feel like rescaling them by error percentage could just negate that outright. What I'd find interesting two things. What I do find interesting is that for some models, you can see making them questions one harder doesn't really affect them, but making them two harder does affect them. And that could also be a property of dataset construction. So obviously this here, you have to put a bit more thought into how you add these difficulty levels. I do believe this particular example here is a good example of how that can kind of quote unquote go wrong or something. I feel like if you're tasked with introducing a new difficulty, you could, if you look at this, right, after 10 minutes, the price drops by this much per minute. You could be just like, oh, let me introduce another price drop after more minutes, right? That's kind of like an added difficulty. Okay. And then someone asks you, well, make another difficulty level. And then you've kind of like, as a human, you're kind of like, well, I've already done the price drop again, so let me think of something else. And then they introduce oh, if your bill is more than $10, you get a 25% discount. So it could be that just by the way they made this data set, the +2 here isn't just twice as hard, but it encourages the dataset makers to introduce kind of like fundamentally different problems. Like here is you have to do a comparison and a percentage discount versus the same concepts that were already in the question present. So in this case, this is just a continuation from the condition that was already there. So it could be that this +1 +2 thing that they are trying to do here is not just, we make it one harder and two harder, but that the two harder is kind of a different nature often. So in a couple of these questions, leading to the fact that for some of the models, making them one harder drops not at all, and making them two harder does in fact drop the accuracy. Second, I want to say that, in this territory here, you are at the limit of what the regular human can do. Like, you give this to like a random person on the street, like this bottom down here, I'm telling you, they, like, a lot of them will have trouble, especially if they have to do it in their head, which the LLMs, they don't get help, right? And especially if you then put them under a bit of time pressure, how many would actually get that? I don't think so. I don't think that a lot of humans, or the humans, would score like 100% here. So again, the question, are humans reasoning? Because if you conclude this here is a good indication of whether stuff is reasoning, because, just adding conditions shouldn't really do anything. It's because you really just have to map it to, and so then I'm sorry, but then humans aren't reasoning. And let's write big papers about, humans aren't reasoning. So I don't get why we expect the LLMs to do that in this case. It seems they're very human, it seems to me. So those are my thoughts on this. And then there's the last experiment where they introduce no ops. So they make these GSM no op. So they just kind of introduce random facts that they have no effect on the answer. Like, okay, you pick this many kiwis, you pick double the kiwis, and then you say, well, 5 of the kiwis were a bit smaller than average. And then a lot of the models kind of fail on that. They say, well, the 5 of the kiwis were smaller, we need to subtract them from the Sunday total. Or 5 of the kiwis, also the O1 or llama here, we need to subtract 5 from the total number of kiwis because they're a bit smaller. Right? So they discover that the models, they don't do well on this no-op dataset, so they kind of drop in performance, even if they use different kinds of multi-shot chain of thought. So by the way, all of these experiments are doing 8-shot chain of thought as kind of a standard for this dataset. So they give them examples in the context. And here, even if they give them examples of the exact same question with the no ops in, just kind of like change the numbers, a lot of them cannot solve the question, even if they have 8 demonstrations of how the no op is successfully ignored, if you will. So the no op here, and then these are where they give explicit examples with no ops, and sometimes even the same question, except different numbers with the no ops in. So you have 8 demonstrations of how to ignore it, and most of the models aren't good at picking that up and are still kind of failing. Noticeably, not all the models. So some of the models like Gemma 2B, if you actually give them a chain of thought examples where they are explicitly shown how to ignore this particular piece of irrelevant information, they can do so, but not anything else. But that's kind of like cheating, right? Because but all the models drop. And this is an interesting bit. First of all, again, if you give this to a human and you put like the irrelevant information like this stuff, a lot of humans would make use of it. A lot of humans would somehow try to get this into their answer. They'd be like, well, what do I do with this? Do I need to subtract it or something like this? Like, a lot of them would. Now, if you demonstrate it to them 8 times how you ignore it, then maybe not, right? But you probably have to explicitly point out, I am ignoring this right here because it doesn't, because I bet you just give this to a human on the street, like at least half of them will somehow do something with the 5 of the kiwis that were smaller than average, like promise. And you come back to the thing, like, are humans reasoning? If yes, then you have a problem with the conclusions of this paper, because most of the humans wouldn't solve the problems. If no, then what is reasoning and how do we define it, and why do we even care if LLMs do it? Because they're doing the same things as humans. And then it's just about, what is it then about? Expecting LLMs to be calculators, to be super formally deriving computers? That's not the point. We have computers. We have programming languages. We have regexes and parsers and all of that, if you want that. So in my mind, I don't know. People love to complain, especially about this, oh, it's not reasoning, it's just pattern matching. But I don't see the point. Another thing, interestingly, that has been pointed out by a member of our Discord when we discussed this paper. By the way, we have lots of paper discussions on Discord. Everyone is welcome. And if you want to present a paper that you find interesting, that's the place. Someone actually pointed out that not only did they really show that LLMs can't reason, because they never define reason, but what they did kind of show that LLMs are really bad at pattern matching, even though their point is kind of, oh, they only do pattern matching. No, they don't. Because even if you give them 8 demonstrations of how to ignore this particular piece of irrelevant information in their context, they can't do it. A lot of them just can't do it. And what better demonstration do you need to show you that LLMs suck at pattern matching? So I don't know. But yeah. Now, obviously, what happened is that their training data makes them want to consider this extra information, and no amount of patterns in their context is overriding this in this case. But still, they suck at pattern matching. So where does that leave us? That leaves us with a bunch of conclusions that the paper has, which again exposes a critical flaw in the LLM's ability to genuinely understand mathematical concepts and discern relevant information for problem solving. Like, yes, but also the limitations of the ability of LLMs to perform genuine mathematical reasoning. But what about humans? Like, the high variance in LLM performance on different versions of the same question, their substantial drop in performance with minor increase in difficulty, and their sensitivity to inconsequential information indicate that, now before you continue, all of these are properties of humans as well. Their reasoning is fragile. It may resemble sophisticated pattern matching more than true logical reasoning, right? So we remind the reader that both GSM-8K and GSM-Symbolic include relatively simple grade school math questions requiring only basic arithmetic operations at each step. These models likely to be more pronounced in more challenging mathematical benchmarks. Yeah. Develop AI models capable of more formal reasoning. And that is where I don't know. We have formal reasoning engines. Why do we need LLMs to do that? Humans suck at it. Why do we need aren't LLMs supposed to be doing the things that humans are good at, but machines were thus far bad at? Yeah, so as we strive to create systems with human-like cognitive abilities or general intelligence, yeah, that's the disconnect, right? Like, I don't know why people assume that these things are any indication of human-like reasoning ability, cognitive abilities, because it seems to me that LLMs are much more like humans, demonstrated by this paper. That's what it seems to me. All right, so enough of the rant. Read the paper in full. They do, like, experiments are good. They have full reports in the appendix and whatnot. I just feel their conclusions are a little bit. Yeah, you can come to different conclusions based on the same data. That's it. All right. Tell me what you think in the comments. I'll see you around. Bye-bye.